Good morning, everyone. So today we will be discussing a new topic. But before that, let us have a moment of silence first for our prayer, no? So may I request everyone to please bow down your head as we pray. Okay, so now roll call muna tayo ng mga names. Let us have your attendance. So when I say your name, you say present sensei. Okay? So Abdullah, Amazon.
A few moments later.
So since we are done checking your attendance, I want to remind you some of my online classroom rules and regulations that you need to um, remember during our discussion. So once again, good morning everyone. So today we will be talking about the Euler's phi function or the Euler's totient function. So
Okay, so here's our objective for today's discussion. So, Mr. Sonano, kindly read our objective. Okay, thank you, Mr. Sonano. So, for a while class, no, kasi naglag yung laptop natin. So, let me fix it first. So, kindly answer the activity. So, I will give you 3 minutes to answer this activity. You may start now. And by the way, you can send it on Google Classroom. So, may naka-prepare na doon. You can just send it after you're done. So, take a picture and send it there. Thank you.
before discussing or defining what is Euler's phi function, let us have a short review first of the proponents of the Euler's theorem or the Euler's phi function. So first is Leonhard Euler. So Leonhard Euler is a Swiss mathematician and a physicist born on April 15, 1707 in Basel, Switzerland and died September 18, 1783 at St. Petersburg, Russia. So Leonhard Euler is one of the founders of pure mathematics. He not only made decisive and formative contributions to the subject of geometry, calculus, mechanics, and number theory, but also he was able to develop methods for solving problems in observational astronomy. So aside from that, he was also able to demonstrate useful applications of mathematics in technology and public affairs. So Leonhard Euler introduced phi function during the 1763. However, he did not at that time he did not have um, he was not able to choose any specific symbol to denote it. So in 1784 publication, Euler studied the function further and then he was able to choose the Greek letter pi to denote it. So then he wrote it pi d for the multitude of number less than d and which have no common divisor with it. Okay, so another proponent is J.J. Sylvester. So J.J. Sylvester in 1879 coined the term totient to this function. So basically, nung kay Euler pa siya, ang tawag lang talaga dito is Euler phi function. But then during 1879, in the time of J.J. Sylvester, he coined the term totient to this function. So that's why now it is called the Euler's totient function or simply the Euler's totient. So the Jordan totient is the generalization of Euler's. A cototient of n is defined as n minus phi is to n, and it counts the number of positive integers less than or equal to n that have at least one prime factor in common with n. So during 1801, Gaius, who was another proponent of the Euler's totient function, he changed the notation or the notation of the pi. So dati yung ginagamit ni Euler is yung pi na symbol and then d. On the other hand, Gaius used the symbol pi and d, but then again, he didn't use the parentheses, and thus it is now called as the Euler's phi function or simply the phi function. So same pa rin yung name, but change lang niya yung notation. Okay, so since we already tackled about the proponents or some of the proponents of the Euler's phi function, let us now define what is Euler's phi function. So Euler's phi function is a function that assigns to each integer the number of positive integer less than the given integer and relatively prime to the given integer. So the function is denoted as like that one there. So it is usually denoted or now it is called as the phi function. So once again, sino yung nag-change ng notation? Okay, very good. It is Gaius during the 1801. So sometimes the indicator is called as the indicator or the totient. So after its originator, the functional notation pi is to n, however, is credited to Gaius. So since siya yung nag-change, of course, credit sa kanya yun. Now, Euler's totient function in number theory, it is an arithmetic function that counts the number of positive integer less than or equal to n that are relatively prime to n. So, same lang no sa ating first definition. That is, if n is a positive integer, then phi is the number of the integers k and the range 1 less than or equal to k and less than or equal to n, for which the GCD is equal to 1. So the totient function is a multiplicative function, meaning that if two numbers m and n are relatively prime, then totient is equals to, or phi rather is equals to phi and phi. Okay, so now for us to have a better understanding, I will present to you an example on how to find the totient or the phi of a number. So let's say for example, n is equals to 9. Then the GCD is equals to the GCD equals 3. And the GCD is 9. The other 6 number at the range of 1 is less than or equal to k. And k is less than or equal to 9. That is 1, 2, 4, 5, 7, and 8 are the numbers that are relatively prime to 9. So therefore, there are 6 phi, or phi is equals to 6. Now, I will show you a table para mas maintindihan nyo, no? But before that, let us discuss first this, another example. So another example is if phi is equals to 1. Since GCD is 1, the totient function is important mainly because it gives the order of the multiplicative group of integers modulo n. Okay, so now I will present to you an example which is yung ginamit natin kanina, no? Yung n is equals to 9. So here, the example says, find phi is to 9. So here is since n is equals to 9, then the number less than 9 are 1, 2, 3, 4, 5, 6, and 7 and 8. So, as you can see in the table, may ginawa tayong GCD and co-prime. So, in the GCD, in here, we will be able to determine whether it is relative or that number, particular number, is relatively prime to 9 or not. So, in the co-prime, we wrote yes, no, yes, no. So, if yes, that means the number is relatively prime to 9. But if no, it means that the number isn't relatively prime to 9. So by the way, class, when we say relatively prime, it is, okay, very good. It means that the GCD is equals to 1. So now, let us check whether number 1 is, or 1 is relatively prime to 9. So what is the GCD of 1 and 9? Very good, it is 1. So that means it is relatively prime to 9. Now, number 2. Is 2 relatively prime to 9 or not? So since the GCD of 2 and 9 is 1, it is relatively prime to 9. So 3. 3 is not relatively prime to 9 since its GCD is 3. So as the definition said, the relatively prime means GCD must be equals to 1. So 4 is relatively prime to 9 since it is equals to 1. 5 is relatively prime 5 is relatively prime to 9 since 5 and 9 the GCD is equals to 1. How about 6? 6 is not relatively prime to 9 since the GCD is 3. 7 is relatively prime to 9 since the GCD of 7 and 9 is 1. As well as 8 since its GCD is 1, so 8 is relatively prime to 9. So as you can recall kanina, it says that the phi is equals to 6. So as you see in the, as you can see in the table, there are 6 yes. That means there is indeed, or the phi is indeed equals to 6. So phi is to 9 is equals to 6. So note that if n is a prime number, so ito dapat nyo itong tandaan, okay? Para mas madali yung pag-solve. If n is a prime number, then every integer less than n is relatively prime to it when pi is to n is equals to n minus 1. Okay? So, moving forward, we will now be discussing the theorems of the Euler's pi function. So, let us find out how many theorems are being introduced in the Euler's pi function. So, the first theorem tells us that if P is a prime and K is greater than 0, then pi is to P raised to the power of K is equals to P raised to the power of K minus P raised to the power of K minus 1 is equals to P raised to the power of K, open parenthesis, 1 minus 1 over P. So now, I have here an example. So still, let us use that pi is to 9. So in pi is to 9, as you notice, pi is to 9 is equals to pi is to 3 raised to the power of 2 is equals to 3 raised to the power of 2 minus 3 is equals to 9 minus 3 equals to 6. So, the 6 integer less than and relatively prime to 9 is 1, 2, 4, 5, 7, and 8. Which means that there are 6 numbers which are less than 2, 9 and that are relatively prime to 9. So, another example, let us try. So, sa first theorem to so we will be proving it. So, since in our first example, it is correct. So, let us try another example to prove whether theorem 1 is indeed true. So, next, let us assume that pi is equals to, pi is to 8. So, it will be equal to pi is to 2 to 2 raised to the power of 3 is equals to 2 raised to the power of 3 minus 2 raised to the power of 2. So what is 2 raised to the power of 3? It is equals to 8. And then 2 raised to the power of 2 is equals to 4. So 8 minus 4 is equals to 4. Which means that the four integers less than and relatively prime to 8 are 1, 3, 5, and 7. So which means that there are 4 numbers less than and relatively prime to 8. Okay, so as proof for number 1, so as clearly, so the GCD of those numbers that are relatively prime, so n is to p raised to the power of k is equals to 1. If and only if p does not divide to n. So there are p raised to the power of k minus 1 integers between 1 and p raised to the power of k, divisible by p, namely p, 2p, 3p, up to p raised to the power of k minus 1 times p. So thus, in the set 1, 2, up to p raised to the power of k contains exactly p raised to the power of k minus p raised to the power of k minus 1 integers that are relatively prime to p raised to the power of k. And so, by the definition of the phi function, pi is to p raised to the power of k is equals to phi raised to the power of k minus phi raised to the power of k minus 1. Okay, so did you get it? Okay, very good. So, moving on to theorem 2. The theorem 2 states that the function is a multiplicative function. So, to prove this, here is the proof of the second theorem of the Euler-Stoichion function. It is required to show that the pi m and n is equals to phi is to m and phi is to n whenever m and n had no common factor, because pi is to 1 is equals to 1. So the result obviously holds either m or n equals to 1. Thus, we may assume that m is greater than 1 and n is greater than 1. So arrange the integers from 1 to m n in m columns of n integers each as follows. So as you can see in the picture, 1 is equals to m plus n, 2m plus n, and so on. Then n minus 1, m plus 1. So same for 2, same process for r, and also for m. So, as we know, pi is to m and n is equal to the number of entries in this array that are relatively prime to m and n by virtue of lemma. So this is the same number of integers that are relatively prime to both m and n. So before embarking, the details are worth commenting on the number of topics to be adopted, because the GCD of QM plus RM is equal to the GCD of R and M. Then the number of the R column are relatively prime to M if and only if R itself is relatively prime to M. Therefore, only pi is to M column contains integers relatively prime to M. So only the M column contains integers which is relatively prime to M. So every entry in the column will be relatively prime to M. So lahat ng nasa column belongs to M will become relatively prime to M. So the problem is one of showing that in this pi is to M columns, there are exactly pi is to n integers that are relatively prime to n. For then altogether would be pi is to n and pi is to n numbers in the table that are relatively prime to both m and n. So now in the entries of R column, where it is assumed that the GCD of R and M is equals to 1, R and M plus R 2M plus R is up to n minus 1, close parenthesis m plus r. So there are n integers in this sequence and no two are congruent modulo n. Indeed, if km plus r is equals to jm plus r mod n. So with 0 less than or equal to k less than j less than n, it would follow that km is congruent to gm mod n, because GCD m and n is equals to 1. We could cancel m from both sides of this congruence to arrive the contradiction that k is congruent to j mod n. Thus the number in the R column are congruent modulo to 0 to n to 0, 1, 2, up to n minus 1 in some order. So if S is congruent to T mod n, then the GCD of S and n is also equals to 1. If and only if the GCD of T and n is equals to 1. So the implication is that the art column contains as many integers that are relatively prime to n, and thus the set 0, 1, 2 up to n minus 1, namely the pi n integers. So all in all, or therefore, the total of entries in the array that are relatively prime to both m and n is pi m and pi n. So now we will be moving forward to theorem number 3. So it states that if the integer n is greater than 1 and has the prime factorization of n p sub 1 to the power of k sub 2, p sub 2 to the power of k sub 2, up to p sub r to the power of k sub r, then phi n is equals to p sub 1, k sub 1 minus p sub 1, k sub 1 minus p sub 2. Okay. Then phi is to n is equals to p sub 1 raised to the power of k sub 1 minus p sub 1 raised to the power of k sub 1 minus 1, close parenthesis, then open parenthesis, p sub 2 raised to the power of k sub 2 minus p sub 2 raised to the power of k sub 2 minus 1, close parenthesis, up to p sub r raised to the power of k sub r minus p sub r raised to the power of k sub r minus 1 is equals to, and close parenthesis, open parenthesis, 1 minus 1 over p sub 1, and then 1 minus 1 p sub 2 up to 1 minus 1 over p sub r. So as a proof, we intend to use induction or R, the number of the distinct prime factors of n. By theorem 1, as a result, R is equals to 1. Suppose that it holds for R equals I, because GCD of, as you can see in the picture, so that one, or in the presentation, no, that number is equals to 1. So in the definition of the multiplicative function, it gives that, as you can see in the picture, it states that it is equal to phi, open parenthesis, p sub 1 over to the power of k sub 1 up to p sub I raised to the power of k sub I times p sub I plus 1 raised to the power of k sub I plus 1 minus p sub I plus 1 raised to the power of k sub I plus 1 minus 1. So invoking the induction assumption, the first factor in the right hand side becomes, yes, basically as what you see on the picture or in the slide or in the presentation. So this serves to complete the induction step with it the proof. So example for theorem number 3. Let us calculate that pi 360 is to 360, for instance. So the prime power decomposition of 360 is 2 raised to the power of 3 times 3 raised to the power of 2 times 5. And the theorem 3 tells us that pi is to 360 is equals to 360, 1 minus 1 over 2, and then close parenthesis, open parenthesis, 1 minus 1 over 3, close parenthesis, open parenthesis, 1 minus 1 over 5, close parenthesis, is equals to 360 times 1 over 2 times 2 over 3 times 4 over 5 is equals to 96. So the sharp-eyed reader will have noticed that save for the totient is to 1, or the phi is to 1 and phi is to 2, the values of phi is to n in our examples are always even. So there is no accident that the next theorem shows. So next is theorem number 4. So in theorem number 4, it states that for n is greater than 2, pi is to n is an even integer. So which has been mentioned in theorem 3. So as a proof, the first assumption is that n is a power of 2. Let us say that n is equals to 2 raised to the power of k with k greater than or equal to 2. By theorem 3, phi is to n is equals to phi is to 2, k is equals to 2 raised to the power of k, open parenthesis, 1 minus 1 over 2 is equals to 2 raised to the power of k minus 1. So an even integer. If it does not happen to be the power of 2, then it is divisible by an odd prime. Therefore, we may write it as n is equals to p raised to the power of k m, where k is greater than or equal to 1, and the GCD of p raised to the power of k and m is equals to 1. So exploiting the multiplicative nature of the phi function, we obtain that the pi is to n is equals to pi, open parenthesis, p raised to the power of k, close parenthesis, pi, open parenthesis, m, and then is equals to p raised to the power of k minus 1, open parenthesis, p minus 1, and then close parenthesis, pi is to m. So which again is even because 2 is to p minus 1. So we can establish Euclid's theorem on the infinitude of primes in the following new way. So as before, we assume that there are only finite numbers of primes and call them p sub 1, p sub 2 up to p sub r. And consider the integer n is equals to p sub 1, p sub 2 up to p sub r. So we argue that if 1 is less than a, then a is less than n, then the GCD of a and n is equals to j not equal to 1. For the fundamental theorem of arithmetic tells us that has a prime divisor q, because p sub 1, p sub 2, and up to p sub r are the only primes, so q must be one of these p sub 1. So hence q is q and n, in other words GCD a and n is greater than or not equal to q. So the implication of all this is that pi is to n is equals to 1, which clearly is impossible by theorem 4. Okay, so any questions? Yes? Okay, so there is none. So since there is none, to group you into 4, so I have already grouped you, right? Same group sa last time. So now what I want you to do is, from your corresponding numbers, so since you're group 1, 2, 3, and 4, from your corresponding numbers, it tells what theorem you are assigned to. So in your group, assume that you are the theorem. So assume that you are those theorem and then create a song explaining the proof of the theorem. So I will give you 15 minutes to do this activity. And then after that, you will present it here in our class. Okay, so now you may start.
A few minutes later.
Okay, so time's up. So everyone, please be ready for your presentation. So group 1. Okay, very good, no? Very creative, group 1. So okay, so now let us hear the work of group 2. So group 2, you may now present your Okay, thank you group 2. So that was very good. That was very good, no? Ang ganda ng composition ng group 2. So let us move on now to the third presenter, which is the group 3. Okay, group 3, you may now take the floor. So very good, group 3. Let us give them a Milo clap. So Milo, 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 syrup ng Milo. Now, we will now hear the last presenter's work. Okay, so group 4, you may now present your output. Okay, so very good, group 4, no? So as you notice, everyone really did their best in creating their songs, no? So very creative. Thank you so much, class, for participating. So before ending this discussion, I want you to study in advance about the Euclid's fifth postulate, since it will be the history of the Euclid, or the parallel postulate rather. So study in advance about the parallel postulate, because we will have a short quiz next meeting. So since there is no more questions,